notice you got two lines, 0 and 1, and then there's a dot for each person's age on the x-axis and whether or not they survived on the y-axis. So you can look at that, you'd say, well, it doesn't really seem to be a factor of age in there, right? It's hard to tell. Don't know if we have enough data points or not, but okay.
So everyone can interpret that? You understand what that means? Right?
Mm-hmm.
Okay.
Okay, so the next cell, this one is looking at the number of nodes that the person had measured positive, what's it called? I'm trying to remember the name of it now. When they're looking for margins after the surgery. So when you look at this, you can see how the number of nodes they found versus their survival plots. Again, I would look at that and say there's not a strong correlation there, but I guess we'll find out. Okay. And then the last one is the third input versus survival. When you look at this, it's just the year they had their surgery. So apparently the year didn't make much of a difference for most of these people. It's just the same thing on both. So is everyone able to get through that part? Able to look at the basic data and take a one variable versus survival at a time, kind of see what the impact is? Okay. So logistic regression. Now we need to start assessing how these variables play into the probability of survival. That's what we're trying to do with logistic regression. So that we can take the data and make some attempt at predicting, did the model give us good results? And if it does, when we get our next set of data, and because the goal of machine learning is so that when we get our next set of data, and we run it through the same model that we create with this test data, we can then say, well, we don't know the outcome of the next person that comes through yet, but based on our model, the probability would say X, Y, or Z. Okay? So here's some of the math background. Whereas in linear regression, we were looking at a linear slope-intercept type parameters to fit to. What we're looking at here is called a log odds ratio. So an odds ratio is the probability of an outcome divided by the probability that the outcome won't occur. And then we take the log of it. So what we do is we then take that and apply that to a linear function, and we'll fit a linear function to the log odds ratio. Now that's a lot of math. You work it out and you get this equation down here called the logit function. And it's basically just a different way of representing the odds ratio, where this exponent t is going to be our fitting term. We're going to try to fit a t so that the logit function tries to map to our probability for this data. Like I said, the links I have can do a better job explaining all the math if you're more interested. So below the math is another cell. I put some blanks in here though. What we did before is you had to start filling in some guesses. So here we have this equation right here. We want to guess at a t that in this case will ultimately fit the age probability. And we have two parameters, b0, which we'll call the bias, and b1, which you can think of as the slope. Except for this t then gets put through another nonlinear function. So it's not a linear function. We're fitting one parameter to a linear function. So in here, go ahead and make some guesses to what you think you should make for a fit, and then run the cell and see what you guys get. So once you create the parameters with the first cell, then you can run the next cell to create your model, and you'll get an outcome. And then on the last cell of the 3 cells, it'll plot it so you can see what the outcome looks like.
Any one of your three single variable data sets. Okay, actually. So while you're trying to do this, it's hard to build intuition, so let's just talk through it a little bit. Let's take age and survival. All right, if we thought age was a really good predictor of, this is how many years survival? 5 years?
5 year survival.
5 years. Okay, if age was a really good predictor of 5-year survival, okay, and young people survived and older people died, what would that top plot look like? What's that?
Step function.
A step function. Right? So again, I'm just drawing what's on the screen. We've got this plot, and this is the either the no or the yes survival, 5 years. And we have people that survive if they're young. This is age. Under ideal situations, it would look like that. Right? I'm sorry that this is not a great mark.
Something a little darker, better.
See if I can see if that's better. Is that better at all?
Yeah, very
Okay, good. So we've got yes and no, and we've got age. Now, we know in reality it's not that simple, right? We're going to get some people who are younger that probably died, so some of these points are going to be down here, and some people that are older that probably survived, so we get some points there. All right? So there's some sort of a blending of those two factors, but under ideal situations it would be a step. All right, so that if you take a look at any of these three single variable comparisons, none of them do a good job predicting. All right, that's the whole problem that we have here. We don't have this thing. This logistic regression attempts to build a bimodal distribution of ones and zeros, recognizing that there's a transition zone where it's not perfect. So it kind of changes this into yes, to probably no to no. All right, so if you plot just that function, that's what you're going to get. Again, semi-ideal. So the better logistic regression works, or a variable works, it's a more stepwise function. Otherwise, it's more stretched out. Okay, so what we're trying to do, which is hard to do when you put in these values, can you go down your model? Okay, so right there, we've got this model, B0 or beta 0 plus beta 1 plus x. We're trying in our mind to figure out, if I have age, what would my values be such that when I put them in and put it into that logic function, it creates a curve like that. So I'm not expecting, I wouldn't expect anyone to do that off the top of their head very easily, but as you play around with the numbers, all right, think about how that would change this. Okay? So that's all you guys need to do for this first step, and then actually Chris shows a really nice plot of the effect that it has.
So if you want to try different parameters, rerun the first cell, then rerun the second and third cell, and just iterate over those 3 cells until you think you got a good guess. Or you feel like you're done. Either way. This is my calculated output.
Okay. So when you get to that second one, the first one creates your data guesses, your model. The second one says, well, how well does that model work? Notice here, this is age, right? We're looking at age one. We're looking at age.
Just age for this
and
one.
Y is the known outcome. These are people that have either survived 5 years or not. It's 1 or 0. And you can see it's getting some wrong. So you take a look at 7 and 8 up there. They're both 0, but the model predicted a 1. Okay? If we keep going down, and we see down here, now we're starting to get where it's a little bit more open-ended. Right? Now these probabilities are predicting, these are very close to, these are very, very small numbers, so they should be 0. But in fact, they're still showing as 1.
That's because I didn't round them. You would typically round these to 1 or 0.
Right. Okay, so start mixing your model up and seeing what you come up with.
Is there one?
The recording doesn't pick up your voice.
The internet called and said that it couldn't hear me. All right, but you guys heard me. I'll just briefly repeat it for the internet, that we're basically trying to fit a curve that's a continuous function from 1 to 0, And as you're tweaking those numbers, you're kind of manipulating this function, and you're trying to get as good a job predicting 1 or a 0 when you know the answer is 1 or 0, and that's basically a probability likelihood of that.
I'm not sure.
How are we doing? Who came up with a good answer? Did anyone get an answer?
What is an answer?
Huh?
What is an answer?
Okay, so scroll down.
I got to step a curve.
Okay, so let's take a look at how does people's number 10, or this row here, not going to be 10 in your case necessarily, how does yours look compared to this?
Much more sharper.
Much sharper?
Yeah, more like more slope.
Okay, good. So a sharper transition. Ideally you want that, but you get a bunch of reds down here and a bunch of reds up there, but not the greens. So if the red and green are on the same side, that's where it got the answer wrong. Because red is the actual and green is your guess. So a number of these it didn't do a good job on. All right?
Yep.
Okay, go ahead.
So everyone okay to move on? You want to ask any more questions about this?
Not good. I can't even get the graph to my mean error. There's something wrong with my model.
So at the end of this, we have the same questions before. How do we evaluate this model? So in this one, these last 3 cells, we're just looking at how many did we get wrong, right? So we make a measurement, and we see a delta, and it's going to tell us how wrong we were for each entry in the data set. And then if we square it and add it, or replace it with a squared, you can see that we get a lot of small numbers until we get a lot wrong. Then we get big numbers. So if you run that last cell, you can kind of get an idea of your sum squared error term. And if you really wanted to play with this more, you could try to see how low you get that number. You want to drive that number to 0 for a perfect fit, but as we already saw, you can't get a perfect fit because of the way the data is, right? So the hope is to get a good enough fit. That's the goal of any of this.
What were the numbers that you used to get that thing?
I used a B0 of 55 and a B1 of -1.
Oh, yeah, let me try that.
Like good one or bad?
So it's
Should be okay, but it's still missed out.
But that doesn't mean that's the only right answers. That's just the ones I used. So
Then you gotta go do the other.
you can at least start with those and see if you want to play with it, move it around.
Because it's on.
So when you do a linear regression, it's easier to kind of guesstimate, what the 2 parameters might be, right? Because you can see where the...
It's even better than guesstimating. When you have linear regression, you can actually solve for the slope and intercept.
Right. But say like for this exercise, right? So you sort of calculate where the probable cutoff or y-intercept is, and then you can eyeball what the slope is. What's the right state of mind in this case, right? Because here it's going to be a lot harder, and then you magically just said 55 - 1. So I'm wondering if you have any heuristic there.
It's model by model, and this one you can look at it because it's 1 input to 1 output is all we're looking at. And the next notebook, when we get to 3 inputs to 1 output, and it's a nonlinear function, there's not a good closed form way of assessing that. So we're going to talk about how to do that. No.
So one thing which we won't get to today, but this is, but it's very relevant to this question, which is what's a good fit and what's your right number. In this binary classification problem, all right, we get what's called a 2x2 contingency table. Who knows what that is? Couple people maybe. So a 2x2 contingency table says the actual answer is either A or B, and I'm going to guess either A or B, And there's trade-offs, because if I guess the right answer, that's good, and if I guess the wrong answer, it's bad, and you can play those things off. So the right metric, the good metric, depends, as Chris was saying, on the model and how you want to trade off this thing called sensitivity and specificity. And in another time when we get further along, we'll do a formal workshop on sensitivity and specificity, okay? But for now, what we have to trust is that we're trying to get this number small. And in this particular data set, it's going to be very hard to do. So I think we'll move on to the next one.
Any more questions before we start the next notebook? If you want to open notebook number 2, in this one we're going to go into implementing an algorithm for this. A little more advanced than what we did, still very basic though. So let me know if you got any problems opening notebook number 2. Okay, so we're going to take the basics of what we talked about in the last one, and now we're going to take it a step further, which is we have 3 input numbers to account for, and all 3 inputs need to be accounted for and incorporated into our prediction of survival, right? So when we did 1 input and we could look at the curve and it kind of made sense, it's very hard to do that with a nonlinear function once we get to 3 variables, or 4, or 5, or 10, or 100. It's not visually easy anymore. And beyond 3, I'd claim it's probably impossible for an average person to look at it and say, yep, this is the right parameters to put in there. So now we have to start leaning on the machine to do more work for us. All right? So execute that first cell, run it. This is going to load the packages we need to get through this notebook. We're going to use the same data we did before, but now we're going to move down to the next code cell. We're going to run that to get the data again, because this is running in a separate kernel. It's got its own memory space, so it doesn't know anything about the other notebook, okay? And then after you run that, run the cell where we create X and Y variables. Okay? All this is doing is it's taking the data, splitting it up into our inputs, the X, and our output, the Y, and it's just grabbing the values. It's stripping away all this table formatting so that it's just working on matrices and vectors, columns, okay? Okay.
No, mine doesn't, oh, yeah, I guess I did it, yes, sorry.
If it works, a little number should pop up, should say in
4.
bracket, some number, bracket, okay?
Mine says 4, right?
Yeah, it just increments it. If you keep hitting run, the number will keep going up. But if you have a number, then it's executed, okay? Okay, so the error calculation. We need to know how we're going to judge how good this model is. For this simple model, we're just going to rely on a sum of the error, where the error is the absolute value between our predicted outcome and the actual outcome. So we're going to say if we're wrong, it's a 1. If we're right, it's 0. We're going to sum up all the 1s. We want to make that number as small as possible. Keep it simple, all right? But we have to pick an approach to calculate our parameters. Like I said, for linear regression, we are able to solve for the slope and the intercept directly. In this, we can't. So what we're going to do, we're going to make guesses, and we're going to iterate. So the approach I chose to do here is called stochastic gradient descent. If you know anything about solving gradient descent problems, you take your current state, you look at a slope, and you move in the direction of greatest slope. You want to find a valley where all your parameters minimize your error, right? So all we're going to do here is implement some equations that move us towards the right answers a little bit at a time. Every time we make a wrong guess, we're going to move away from our current state to the next guess of the parameters and then rerun and see what happens, all right? Does anyone want to ask any questions about gradient descent? I know if you haven't done optimization stuff, you may not know what I'm talking about.
I imagine he can get you in trouble sometimes if you pick the wrong,
If you don't start in the right spot, you will
Yeah.
get stuck somewhere.
yeah.
Yep. Yep. And there's a lot of advanced features built into the Python tools that can do this more accurately and more rigorously than what we're going to do here. But this is just a demo how to do it. So what we need is some equations for updating the parameters. Now we have 3 inputs, but we need that bias term, the one without an x attached to it. So we have 4 parameters we have to solve for, okay? And then up here is how we're going to do it. We're going to calculate a new value for the parameter based on the old value, and then we're going to take whether or not our prediction was right or wrong. So we're going to subtract the actual and the predicted output. We're going to multiply by a learning factor, which is just a number we pick to try to improve our descent to the right values, and then multiply by the input that we're trying to solve for. So for example, for beta 1, we're going to multiply by input x1, which in this case will be age, times the difference between our actual and predicted output and our learning factor. And then we're going to adjust our beta value based on that. Make sense? So it's just a simple, we're just going to loop through this now. Okay? So,
Why is it the same factor for all 4 variables?
simplicity here. You could make it different if you wanted.
Yeah, why don't
And you could adapt the factor as you go too. You can speed up your convergence or slow it down. And if you think you're moving too fast, you can decrease it. And if you think you're moving too slow, you can increase it. So there's actually all sorts of methods of adjusting that learning factor dynamically as you're doing your solution, okay? So it doesn't have to be static. We're just keeping it simple with this one though, but that's a good question because it doesn't have to be the same. It doesn't even have to be constant. Okay, the way we're going to put the algorithm together, we're going to take our training data or our input data set. We're going to split it into 2 pieces called the training data and the test data. So the training data we're going to use to calculate our parameters, and then the test data portion we're going to run through the model with the parameters we calculate and calculate our error. So that's how we get our error values on the test data, not on the training data. And I think Dave will touch a little bit on why that's important when we get into the next notebook that Dave has. Then we're going to make some initial guesses for the parameters. These are just, we're going to pick some starting values for beta. Then we're going to go through 2 loops. We're going to loop through the data item by item, and with each step through the data row, we're going to adjust our parameters. So we're going to start out with a lot of error on our first entry in the data table. By the last one, we should have less error. One trip through the data, we call that an epoch, okay? And then you're going to run multiple epochs. I picked a number 10. You can pick any number you want. And at the end of each loop through the data, you're going to calculate your error. So you're going to run through the data once, calculate your error, run through the data again, calculate your error, and then we'll move through that a number of times, and then at the end we'll profit. So there we go. So this next cell here, we're going to run that to create our training and test data. So this function is built into the sklearn, the scikit-learn package, and it will take your input data and it'll give you a percentage based on this number, where I say test size is 0.3. The test data will be 30% of the number of samples we have. Training data will be the rest. It randomizes the order so that you don't have any sort of confounding factors with the sequence that the data was generated in the list. And then it spits it out to 4 variables that we'll use for training and testing our data. So run that cell. Then we need a couple functions to help us through all this. First function here is to calculate our output. So we're going to calculate survival. This is where we're going to do the math that we talked about before. So on the first line, we calculate a t, and that's just going to be a sum of our betas times our inputs. It's just beta 0 plus beta 1 times x1 plus beta 2 times x2 plus beta 3 times x3. And then that t is going to plug into the logit function, and that's going to give us a parameter y. And then we're just going to quickly check that y is between 0 and 1. Why do you think that is? Why are we going to check if it's between 0 and 1?
Because we need to be as near as 0.
Yeah.
Yeah, because it's a probability, so it has to be between 0 and 1. Okay? Excuse me. Okay, but then in the return line, I left it blank. What do you guys think should go here? What value should we be returning?
Y. Oh, T.
Y?
T.
Nope, you're right, it's y, but it's not just y.
T and Y.
Y is the probability, but this function's calculating whether or not we predict a survival. And survival can have what values?
1 and 0.
0 or 1. So you have a probability between 0 and 1. We're going to round it up or down to 0 or 1. So you have to round it here. So the way to do that is we use the numpy. In this case, we just refer to it as np. Then we round it with a function called a round. And then inside of that, you put y. Well, we call it y underscore, but y underscore. So you want to put that in there. And what this function will do is it'll say, okay, the calculated y is 0.6. I'll round that up to 1. Or if the calculated y is 0.4, round it down to 0. So our output will always be 0 or 1, which is what we want. We want to predict survival or not survival, right? So after you guys type that in, go ahead and run that cell. Now that just defined the function. We're not using it yet. Because, what's that?
What did you say I'm supposed to type in?
np dot a round right here,
Yeah, okay,
this guy.
okay.
np dot a round, so the numpy package, a round function, and you pass in the y underscore parameter we calculated, okay? And the rounding just takes it up or down, 0 or 1. Make sense?
Yeah.
Okay. Now, we're going to create another function. This function is going to take in our current parameters, our current predicted output, our actual output, and the current input values, and the learning factor, if we choose. By putting in eta equals 0.2, it's got a default value, so you don't have to pass in a learning factor number if you don't want to. And then this function will just calculate the updated values for beta. So this will run through the math equations I showed earlier. What this does is it checks the actual versus predicted, and then it updates beta 0, 1, 2, and 3 based on the difference between our actual and predicted and our learning factor and our input values. So it's just 4 simple linear equations in a row. And then at the end, we return our new values. Our new parameters are returned. Does that make sense? Anyone have any questions before? If it makes sense, go ahead and run the cell. So now we have that function defined as well. So we got 2 of the functions we need. Need 1 more function. We need to be able to calculate our error. Like I said, for this one, all we're going to do is sum up the number of mistakes we made. That's all this function's doing. It's checking whether or not there's a mistake and then summing them up. So it's going to count the mistakes for us. So go ahead and run that cell. So we got the 3 functions we need. And so now on the last cell is where we actually run all this on our data. I left some blanks in here. So we get a couple of things we need to be able to pick that we can vary. First one is the number of epochs we want to run. You can pick a number. I'd pick some between 5 and 10. Doesn't have to be more than 10. Pick a number, put that in there. I'll do 10 just to show you what it looks like. And then eta, that's our learning factor. You can pick any value you want. I would recommend from the 0.1, 0.2 range. If you want to try 0.01, you can do that. If you want to try 0.7, you can try that. I wouldn't go over 1, but you can try different values there if you want, okay? For this example, I'm just going to put in 0.1. All right. So we're just calculating the length of our training data in the next line, and then we're creating our initial guesses at our betas. So in this row, I'm putting in my guesses for the betas. Beta 0, I'm guessing is 0. I don't know what it is, but I think that's a reasonable guess. Beta 1, I'm guessing is 55. Beta 2, I'm guessing at 60, and beta 3, I'm guessing at 1. And like I said, these are all just guesses. They could, if you think you can look at the data and make a better guess, go right ahead, change these numbers to whatever you think is reasonable. The next line, I'm just creating an array to keep track of our errors at the end of each of our epochs, okay? So like I said, one full trip through our data sequence is one epoch, and we're going to calculate our error at the end of each epoch, all right? But then we're going to run multiple epochs and look at what happens. So in our first for loop, our outer loop, we create our two arrays, one to store our predicted training data outputs in, and the other one to store our predicted test data outputs in. This uses a function called zeros like. What that does is you pass it in an array, and it creates an array of zeros the same shape and dimensions. So it can be a column array or a row array. It'll make it look the exact same as the array you pass it, but it'll populate with all zeros. So it's a good way of initializing an array that copies another array. All right. In this for loop right here, for I in range n, this is where we're going to step through our data row by row. The first line is inputs. For this row, we're going to get our 3 inputs. So that's what that line's doing. It's getting our 3 inputs from the matrix of inputs. Then it's going to use our calculate function to make a prediction for that particular row. What's our predicted outcome? Survival or not? And then the third one, it's going to update our parameters. So in the third one, you're running your update parameters function to update your betas based on your prediction. In the next for loop, we're going to do the same thing again, but we're not updating beta anymore. The next for loop is just to check our current betas against our test data. This is where we're going to calculate our error, okay? So we've gone through our data, training data once. We think we have pretty good values for beta. We're going to test those values against our test data, which is a separate set of data. We split our data up into training and test. And then we'll calculate the error based on how that test data performs with those beta values. Then we're going to print our beta values. We're going to store our error for that particular epoch in the array, and we'll loop through our number of epochs, and then at the end we'll print our error array as well, so we can see what happens. So there's about 92, when you run this, you should have about 92 data samples in your test sequence, and if you can do it completely random, about 58 of them you'll get wrong. So let's see how we do. Go ahead and run it. Depending on what you pick for epochs, it may take a couple seconds.
You've got it there because of this. Yeah.
So for my guesses, you see here that as you look at your betas, it's not changing very much. So my guess is either learned too quickly or it found a minimum right away. And then the error after each epoch ended up staying the same. But at 34 errors, I'm doing better than random guessing. So if you divide that 34 by 92, you get, something on the order of 30-some% error rate. So go ahead, play with the number of epochs and your learning factor and see what other results you can get. So I'm going to change it again to 0.01 and see if that changes anything. No, see, it doesn't like that. So we'll try 0.3.
What's the question?
Yeah.
So,
Oh, yep.
so we're using the same source data file, and then we randomly put it into test and to measure, I guess it is.
Yeah,
Or
train and test, yep.
test. Is your train and test going to be the same as mine?
Nope, and each time you run it, if you go back up to where we generate the train and test, each time you run it, it'll re-randomize the samples. So your results can be different than mine because the samples are put in a random order each time and it picks a different set of random samples for the training versus the test. So you could pathologically end up with the hardest to fit data in one and the easiest to fit in the other. So you may have to run it multiple times to actually get some idea of how close you're getting to your answer. Does that make sense? Any questions? No?
I got a question.
Yeah.
What's the difference between a hard fit and the ease of fit data?
Well, there's a lot of things that go into hard and easy to fit. Depends on
Like you said, depending on how it gets randomized.
Oh, well, all the data is going to have a certain amount of noise in it, right? And some data is going to be noisier than others. And you could pathologically randomly grab the ones with the most noise in them for your test set. And so you train to the stuff with less noise and then test with more noise and end up with a higher error rate, or vice versa. You can end up with more noise in your training set, less noise in your test set, and your error rate would be optimistic. And if you train too much, then you can end up with overfitting, and then you get errors because you're trying to actually fit to the noise and not to the actual data. So you don't want to overtrain either.
So the issue of noise is itself its own study. You can think of noise in a lot of different ways. One way to think of noise is, in fact, truly random noise. That is, it doesn't correlate with anything. I give you a noise number, and you give me another number, and then I give you another number, and they're completely unrelated. That is true random noise. And noise isn't characterized by any one value, but by the distribution of values that it can represent. When you're dealing with noise, truly noise, then I know that these strategies are well suited for dealing with that. So one way to think of easy and hard is hard things have a lot of noise and easy things have a little noise, where that's truly random noise, and you can address noise through things like averaging and repeated running. All right, then there's other kinds of noise, things like confounders or bias, which is if you have an instrument and your instrument is always giving you the wrong answer by a fixed amount. It's always off by 3 volts, okay? You got your voltmeter, it's always off by 3 volts. That's a bias in the data. That's actually pretty easy to manage as well, because the linear regression model has a specific term for that. But what if there's some value that is correlated with your signal, but you didn't measure it? That's called a confounder, and that's actually really, really hard to manage because it looks like noise, but in fact it's not noise. And that really confuses the model, because the model can start to predict the confounder, not the actual model parameters. I'll give you one example and then I'll stop talking. So they did some research a long time ago, and they studied people that were drinking coffee and then people that died of heart attacks. And it turns out in like the 50s that drinking coffee correlated with having heart attacks. That's not good, right? I mean, I drink plenty of coffee, way too much in fact. I don't want to have a heart attack from that. Well, it turns out that they didn't measure one really important variable, which we call a confounder, and that is smoking. It used to be that when you drank your coffee, you smoked. That's what you did on your smoke break or your coffee break. And it turns out, in fact, it was the smoking that predicted heart attacks, not the coffee, but because they didn't measure that, they thought that the coffee was. Well, machine learning models, if you don't give it data, it's got to try and guess, and it can pull out some of those features. And that's hard data as well. All right?
All right, so now I'm going to pass it off to Dave to do 2 more notebooks. So,
Quick question.
Yeah.
Go on. One second. No, you mentioned in the 50s. It seems to me that different decades, probably the data is going to be different, right?
Absolutely. So the year in which data was collected and the instrument that was used to collect it can vary and add in its own kind of confounding factors. So you have to try and correct for that if you can.
And if you're going to use it for medical purposes, for instance, or giving advice to whether you should drink coffee or not, you really need something that's appropriate to what you're doing and the time frame you're talking about. So recent data is important, right?
Absolutely. And understanding when your data was collected and how it was collected is incredibly important. And there's techniques to correct for those factors to some extent. Sometimes you can't, but you can try. So, all right. It is 7:30, and I'm about to start 2 notebooks on penalized regression. How are we doing? Everyone's hanging in there? Does anyone need more caffeine? No heart attacks, just caffeine?
Don't smoke though.
Bio break.
All right. I
Use the mouse.
have to use this mouse over here. Okay. So I'm going into notebook number 4. This is the bias variance problem. In this, we're going to go from some interactive stuff, and then there's going to be math, and you're going to get really angry and pull your hair out, and then we're going to ignore that and go back to interactive stuff, okay? So just bear with me. So the bias variance problem, all right, good. So the bias variance problem is one that we face quite a bit. And what I want to do is first talk through that and then talk how penalized regression helps address that, and I'll define that. So inside this notebook, notebook number 4, I got to use this keyboard too. So we're going to go ahead and go to the first window and run that. All that is doing is loading up stuff. The other thing that these in particular do, I'm going to be using the predefined packages in Python for solving problems. We can do it the way Chris did and the way that I did in our previous lecture, where you get the hands-on experience. Thank you so much. But in this case, we're going to try and do it a little bit quicker and use the built-in tools so you can see the power of those. So you can actually execute both of the first 2 cells. These are loading your libraries and then drawing pretty picture things. Okay. How many people have seen a figure like this with bullseyes? That trades off accuracy and precision, right? Okay, so we've got this notion of accuracy. Who wants to tell me what accuracy is? Someone raise their hand. Gabriel, what's accuracy?
It's a metric to measure how close you are to the correct value.
Right. So accuracy is how close are you to the correct value. Okay? Someone else raise their hand. Who else raised their hand? One of you 3 guys did for seeing these. You want to do it? Okay, what's precision?
Precision is when you can hit all your data in the same cluster.
All right, it's how consistent is repeated measures. Okay, so if you take a look at the chart, when we have high accuracy and high precision, and we're shooting something, we've got a nice target. That is not what I look like when I deer hunt. I can tell you that right now. When we have high accuracy but low precision, it's right around the bullseye, but it's really spread out. Fortunately, that's not me either. If anything, I'm probably low accuracy and high precision. I'm really good at missing and pretty precise about it. So this is me, low accuracy, high precision, and then there's low accuracy and low precision. And as a matter of just getting some intuition on that, if you go down to the next cell, we got this cell here where we just have to run, that sets up our little functions. So there's a function to create a bullseye, and there's a function called shotgun that will put points on that. This next cell is the one I want you guys to look at. So I say for a number of points, I'd like you guys to enter an accuracy and a precision, and then plot that out. And that will generate your very own target, okay? So everyone just take your time, put in for accuracy and precision a low number and a high number for each one of those.
Low number and a high number.
So as you're doing it, this is the one I generated. High precision and high accuracy, it's not bad. I'd be happy with that, right? Even my high accuracy, low precision, not too bad the way I put it in. But it sure gets off when we start to get down here, right? So bigger numbers are a bad thing here. In fact, I think that's the question I ask you. Oops. So there's two questions as you guys are doing it. The second one, think about when I said low number and high number, what those mean. Okay, so if you put in two fairly small numbers versus two very large numbers, what do you get? So think about that. So how many people here think, does a low number correspond to a low accuracy or low precision? Does a small number mean poor or low accuracy? Try it out. Put in a couple of low numbers, take a look at your plot, put in a couple of high numbers.
Integers are decimals.
I think it can be either.
Okay.
No.
Low mean accurate.
So low numbers means high accuracy. Okay? What about precision?
Same.
Same way. All right? When we're talking about this, we think first and foremost in terms of accuracy and precision, but mathematically we can describe those as bias and variance. Okay? So it turns out a low accuracy is a high bias and a low precision is a high variance. And we can go back to our picture and make sure we understand that. So where's my picture? Here's my original picture. So if I have low bias, that means I have high accuracy. That means the distance is small between the center of the bullseye and the center of my points. All right? And if I've got the other way, the precision, if I have high precision, it means they're clustered. The variance, the variation in those bullets is small. Okay? So bias is the distance away from the center, and variance is the spread. Okay? So the same concept, one's just kind of inversely related to the other one. Now, real quick, for anyone who's spent some time thinking about this, how might you address accuracy and precision? How do we address accuracy?
Average.
What's that?
Average.
Okay. Average? Who's thinking average? Okay, what about how do we address precision?
Median. No.
So precision, if we want to tighten up our cluster and get near the middle, all right, we're going to average. If we're offset, we're going to calibrate. We're going to calibrate back. Okay? So now we have, this is my one math one for this notebook. We're not going to spend a lot of time here. If we go back to linear regression, you can see that top line there under linear regression. Y equals mx plus b. all right? We're trying to fit a line. Nothing magic about it. We're trying to guess at M and B given some input X and some known output Y. However, that's ideal conditions. In the real world, we have this error term. All right, you see the E there. And error is what we were just talking about. Error can be random, it can be structured. I'm going to be super lazy and call it random. Okay? And it's what's, in this case, we think of it in the simplest sense, is normal random, which means it's a random number that if you add up all the if you look at all the random numbers, there's a normal distribution, a Gaussian that fits that. And the nice thing about that is you can describe a Gaussian by two parameters, the mean or the center of the Gaussian function and the standard deviation, which is how wide or narrow. Now, interestingly enough, mean sounds an awful lot like getting close to the middle of the target, and standard deviation says an awful lot about the spread. So, maybe we can take advantage of that. So, we've got our function, the normal distribution, we got our mean, our standard deviation. Now, if we have this error term, we have to carry it now down into this expanded form of our error calculation. And this goes all the way back to linear regression. Look at the other slides from last time, where it's the difference between my actual and my predicted, but now I've got this term, this error term, and that's a problem. I want to be able to control for that. So what does this mean in terms of model development? Well, I'm going to give a model. This is a model that I created called Dave's Daughter's Dates. All right, I have 3 daughters, and when they go on more dates with more boys, my mental well-being goes very much lower, okay? I'm not a big fan of this. All right, so I created a model of what that would look like, the number of boys that my daughters have dated versus my mental well-being. And I also have the linear regression function, which is just the standard linear regression that we learned about last time with some stuff around it just to pretty it up, okay, some window dressing. So we're going to run that. And all that does is set up our functions. Now here, Dave's daughter dates, I'm going to plot this. So as it turns out, if it's just 1 or 2 boys, I got pretty good mental well-being, but it drops dramatically and it kind of falls off. Like after we get to 5 boys, I'm pretty nervous about this whole thing. Okay, and what I want to do is a function, I want to create a model that predicts that so I can start to limit how many dates they go on for my own best interest. All right, so let's go ahead and do that. Now here, this is just for some plotting stuff. You don't have to really care about it. What I'm going to do is I'm going to plot more and more complex models. Now, so far we have talked about the linear model, right? Good old-fashioned line. So the linear model, in this case, I hope it goes down like that, but the data doesn't really feel like that, right? So can I build a higher order linear function to do this? What's the next best function after a line?
Quadratic.
Quadratic, right? Now, it turns out that even number quadratics are a bit of a problem because their symmetry is funny. They only do, U's and stuff. I want something that maybe goes like that. So maybe I could try and fit something like that. So that's an odd order polynomial. So I'm going to start to build more and more complex models with higher order terms. All right, and so actually what this does is just that. This is going to step through a number of different models to plot. Let's go ahead and do that real quick. It's a lot easier to look at than it is to read.
Wow.
Okay, so what this does, and we don't have time to read through the code, what this does is it generates more and more complex models. I still have just one variable, the number of dates that my daughters go on, but I can fit the data better and better and better each time. All right? So that sounds like that's really promising. What's the risk of doing that? Why don't we like more and more complex models?
I don't like them.
What's that?
I don't like them.
Yeah, you don't like complex models. I don't either. It hurts the brain. Go ahead. Overfitting. So this is the situation where I can build models to fit almost every single one of my points, but that point here, that's probably noise, right? And that's probably noise. It's not the straight line, Because I guess at some point, it's okay, my daughter goes on one date. But more than 5, I'm feeling not so good, but I'm already at the bottom there. So it's something in between, all right? And so we have this issue that we can make more and more complex models to get a better fit, but then it overfits it. All right, so there's another, if I take a look at it, and this is a complex figure, I apologize for that. What this does is this looks at the columns across the top are my coefficients. Okay, these are the, if I write this out, I got y is equal to b0 plus b1x plus b2x squared and so on. Okay, those are my coefficients. And then these are my model powers. And what you see is as I get larger, I get more and more coefficients, and I fit the data better. Just look down the curve here. We start at modest small numbers. Look at how these things blow up. Coefficient 2, as I get bigger and bigger, is getting larger and larger. Why? Because it's trying to capture more and more information, okay? It's trying to use these weights to make more and more decisions. So I'm getting a lot of variables, and we don't like complex models, we just talked about that, and they're becoming really big values. If you look at any one of them, it's actually quite unstable. Okay, so we don't like that. So the questions are, as the model gets more complex, there are more model coefficients that are fitted. We don't like that. And they're getting larger. Also, as we get closer and closer to perfectly fitting the data, we are now fitting the noise rather than the signal. So all the things we just talked about. So this is the end of this one. You can go back and look at it. The whole purpose is to play out in your mind what this trade-off is between bias and variance and what overfitting happens when you build more complex models. All right? Questions? The next one's a little bit more interactive. Okay. So if you go back and you open up the next one, called Penalized Regression, and this is where you can pull your hair out because of all the math, but trust me, you can ignore most of it. What we're trying to do here is deal with not building overly complex and overly overfitted models. All right? Simple, stupid, good, that sort of thing. So again, going back to penalized regression, we got our basic equation. We just talked about building a higher order equation. Now it's still univariate, meaning there's one variable we're trying to fit, but this applies to high order equations when you got 10 and 20 and 30 variables. So if we take a look at the next line down, we can build as complex of a linear model as we want. We can add as many coefficients as we would want to that data. That looks terrible. All right. However, even when you do that, you have the same kind of a function here, right? Or the same kind of error function, which is simply the difference between the actual and the predicted. But now, if you take a look at that, you have all these terms that you're trying to do. Now, if we were doing, doing like we did last time where we solved that explicitly and write all the derivatives, you guys would really be angry with me. And I would hope that you would have both low accuracy and precision when you throw stuff at me, because no one would want to do that. Because the equation there is pretty messy, right? It's a bunch, you've got the sum, and there's all these terms, you got to get derivatives of that. We don't want to do that. That's where Python's going to help us out. But nonetheless, that's the concept. And we already know we have this issue as we build more complex models. We have way too many variables, and those variables are blowing up. They're becoming unstable. So the question is, how can we simplify that? Well, there's a number of techniques called penalized regression. And what they do is they try and manipulate those weights to be more manageable. So if we look right here, everything to this side is the same, but I've added this term. It is the sum of all of those weights squared. Now remember, we're trying to minimize the error. What happens if my betas get really, really big? My error goes way, way up, right? That's bad. And in fact, it does it to the power of 2, which means that I'm going to dominate based on those weight values way more than even the difference in the actual versus predicted. So that's a really important factor. That says when I optimize part of my optimization has to be that these numbers are small. Okay? Now there's another one. That one is actually called ridge regression. And you can just see everything expanded right here. This expansion is just, again, to remind us that we don't want to do math on our own. That's why we have the Python library to do it, because I wouldn't want to show you those derivatives to get that solved. Because now I've got betas both in here and out here. Oh, what a mess. However, it's a good idea, right? It forces the numbers to be small, and that's what's called ridge regression. All right? The purpose of ridge regression is that you've got to work really hard to create a large beta value. It's got to really justify a low error. Otherwise, it's going to cost you too much. So that tries to shrink those values down. There's another term for this. It's called L2 regularization. Now that you've read it, you can forget it. Just when someone says it, say, oh yeah, I know exactly what that means. Dave said so. It's not that important, but that's what it's called. Now, there's another technique, which is now at the top, I can't reach it, that's called lasso regression. And instead of taking a square of the number, which really tries to shrink it, it takes the absolute value of that number. So what does that do? If I've got a large negative number and a large positive number, it shrinks it towards zero. It forces things towards zero. And lasso regression is really good, because if I have a parameter, one of those betas that's at zero, then I can throw it out of the model. It's not contributing anything. So not only do I want them small, but if they're so small they go to zero, I get to get rid of it. And that's another bonus. So I've addressed both large numbers and the simplicity of the model by getting rid of some of the weights that don't matter. And in fact, someone was smart enough to say, why don't we put these together? Why shouldn't it be small and throw out weights that we don't want? And that's called elastic net registration. Okay? And all three of these are available in Python sklearn. Okay, so we're going to take a look at some code here. First thing first, we just run all of our imports. Oh, I'm sorry, I did miss one thing. Right here, what is this lambda? There's a lambda that pulls through this thing. It's right there, lambda, it's right there, lambda, it's right there, lambda. Lambda is a weighting factor. How much do you want to control your error metric by the error of the coefficients versus the actual versus predicted? If those were equally weighted and you've got really large values, then your beta kind of take control and you never actually minimize, you actually collapse to zero. So lambda is like a tweaking parameter. No different than gradient descent has a step size. This is almost like a step size for the error metric. All right, how big or small do you want to weigh the errors or the coefficients themselves? All right, so if you haven't yet, run your import. Notice that the import, we're looking at the Boston data again. If you go back to our previous lecture, you'll see Boston data. We're going to use that train test splitting again. We've got linear regression, which we've looked at, ridge, lasso, and elastic net.
Line 7, the important issue.
What's that?
Line 7 have an important issue. Didn't find that library.
We're using a different version than I am. That's a shame. Hey, Brian, is there any way to fix that on the fly? I have no idea, because it should work. Cross-validation. Actually, you know what? Your model should have that. Where's, which one did you do train test split on? Was it this one? I must have a... All right, so I'm jumping around. We'll fix this together.
Model selection.
So here, it says cross-validation. That is the version that I have. I'm using the wrong thing. Let me get it for you. It actually should be under model selection. So what you're going to do is after I put it up here, you guys can just type it in. So here, the second one down should say model underscore selection. And I hope that works. That should work. It does. So I apologize at that. You just have to put in the word model selection versus whatever I had there. Cross-validation. Just different versions of the package. Okay. Okay. So we're going to use penalized regression in Python. We're going to start with this Boston housing project. Remember, this is where they collected a bunch of variables from housing in Boston, and they want to try and see what predicts the value of a home. So we're going to load that up, and we're going to put it into a data frame. Remember, a data frame is that Excel spreadsheet, and it has all these variables, which if we go back to our original lectures last time, we'll see what each of those means. And our target is to get price. So we got this thing called price. There's my price right there. And actually, I'm going to split it into two tables. This is the original table of those values, and there's the price table. That tells me what the output price is. And I'm going to build a model using all those variables. Okay?
Could you get that where it says model selection again? I didn't type it in.
Absolutely.
Yeah.
Right here.
Okay, it's that line.
It's the second one down.
Where it says cross-validation.
Cross-validation, and it says,
Model.
Model underscore.
what is it, dot model selection, right?
Yeah, there's sklearn dot model underscore selection.
Yeah, so you want to delete the cross underscore validation and type in model underscore selection.
Okay. Well, that's good, because I'm almost ready to do that. And the model selection, 2 words?
Hey, there's an underscore between them.
Okay.
Chris is going to come look, and I'm going to actually go just a little bit further down to keep moving. So we have the input data, which has to do with the age of the home and the neighborhood it's in and all that, tax brackets, and the output variable, which is price. And just like Chris did, we're going to split this into training and testing. Just like you learn something in school, you first learn on some examples, and then you take a test and see how well you did. No different than that. Someday we'll go into a whole lecture on training and test strategies. All right, now here's a little bit of chunk of code. We've got our linear regression, and we did this before, so this should look similar to what you're expecting. And then we do a fit of the training and test. Now, great thing, if I want to do ridge regression, I just call ridge regression. I don't have to do all the math for you guys. I can just call ridge regression. So right below linear is ridge. Remember, I need that alpha, that step size. I do a fit, and I'm going to do it for 2 different alphas. So small step size of 0.1 and big step size. And then I'm going to take those outputs and I'm going to look at how well it does on the test data set. So there's training and there's test. Let's see how it did. Well, so this is a score. We want the score to be high in this case, actually, not low. If we do linear regression on the training data set, we get about 75% correct. All right, we're able to fit that well. Percent correct is the wrong term. That's the R-squared value. So we get a R-squared or a correlation of 75%. When you run it on the test data set, it has a value of 71. So pretty good. I mean, that linear regression is not bad. However, let's take a look at the ridge regression. So I said a small alpha. That means the step size is really small. Turns out, I get just about the same answer. Look at that. If anything, it does just a little bit worse.
What's a small alpha? What number did you?
Oh, alpha is this thing right here. I'm sorry, it says alpha equal 0.01.
Okay.
That's a small number. And alpha equal 100 is the big number. Okay, so here, the numbers are actually quite comparable. Well, that's because I didn't really change much in my ridge regression, and we'll look at that in a second. When I go to the higher one, the 100, alpha of 100, we actually do a little bit worse on training and a little bit worse on test. How do I feel about that? I'm showing you worse numbers and telling you you should do this. Well, a couple of things. Number one, if I take a look, what this plot does, the next line down, is this is all those coefficients. And you can see there's 3 coefficients that I'm not controlling for here in linear regression, and they're way out of whack compared to everything else. They're really big numbers. They're going to dominate my model. All right? So I can get almost the same answer with coefficients, those 3 blue dots in the middle, that are much, much smaller. What does that mean? I'm going to have a more stable answer, number one. Number two, as I kind of loosely explained, that by having smaller numbers, I'm not going to overfit as much. So yeah, it's a little bit less effective, but it will most likely generalize more. In fact, I might be able to take this model and use it in New York or Washington, D.C. I don't know. But it's more likely to work on a larger data because I've controlled for overfitting and I've reduced the size of those weights. Okay, so small trade-off. And this is part of what you do when you're doing data analytics. You're trading these factors off. It is 8 o'clock, and I'm just going to rip through this a little bit more and then give you guys a homework assignment. So I showed you ridge regression. Here's lasso regression. If you read it, it's going to look exactly the same. I do my linear regression. I call lasso with the small number, lasso with the big number, and then I do training and testing. Let's run that. Now here, interestingly enough, I should get the same answer, and I do, about. Here, it's a little bit smaller number. I mean, it's not quite as good. I'm only at 73 and 69 for an R squared. And if I go to an alpha of 100, it does very poorly. It's only, 25% right. So that's not good. What have I done to get that really bad answer? Well, I actually got rid of a whole bunch of coefficients. So here, originally there are 13 coefficients. Just adding a little bit of lasso regression gets it down to 12. If I put a lot of lasso in there, then it drops it to 2, but now I don't fit the data at all. So maybe I need to try something in between. Let's see if I can build a simpler model and still get pretty good results. I don't know. So here, look at this. I dropped down to 4, and I'm about 50-50, so not great. All right, this is not a particularly good data set for this, but it does show the decrease in the number of weights, of coefficients, and we can do that same plot. And what you see is that, again, they're shrinking towards the middle, and in some cases, if they're at 0, we throw them out. So I can build a simpler model. What does that mean? That means that I can compute it faster. I might be able to compute that model on an embedded device if I want to do something in real time that I couldn't do before because it's too complex. If I have thousands of variables, if you're doing bioinformatics, genetic studies, you've got thousands of variables. You don't want to keep them all in there. You want to break it down to just the most important ones and keep those around. Now, here's the homework assignment for you guys. So this last section here, time for some real. See, this is how you edit your documentation. All right, time for some real work to get done. So this is, I've now kind of talked through it. You've got some example codes. This is a different data set. So someone took a bunch of mammography scans. These are scans of women's breasts who are at risk for breast cancer. And they took lesions on the images, and they measured features on those images. Are they dark? Are they light? Are they round? Are they square? Are they smooth? Are they textured? All right, and they loaded those up into a data set. It's called the breast cancer data set, and basically it predicts breast cancer based on the imaging data. And what I have here, I'll just talk through it and then send you guys home. We're going to load that data set. And what you can see is that there's 30 different variables. Last time it was 13. Here's 30. You got radius, how big is it, texture, perimeter, area, smoothness, all these different features. And what I have here is a little bit of code that does linear regression. We already know that. That's something that should be second nature. If I run linear regression, I use all 30 features. I get, on my training data set, I get 78% correct value, and on my test data set, it's about 73%. Now we have ridge, lasso, and elastic net. All right, and then plot your findings. So your homework assignment, if you choose to do it, obviously, is to play around with some alphas for the ridge. All right, then figure out how to go from the ridge to the lasso, and I'll give you a tip, copy and paste, and that's how simple it is. And then do the same thing for elastic net. And compare if the models get simpler, which they should in terms of number of coefficients possibly, and smaller values, and see how that trades off against your accuracy, or your final score, which is an R squared. And then plot those findings. All right? If you can do this, then you've got penalized regression down. There's nuances, but this is enough to get you guys to be doing it yourself. Okay, we're 5 minutes past 8. What other questions can I answer? Otherwise, people can wrap it up. Yeah.
What if, so you're saying that you want to trim down coefficients that are largely responsible for the prediction. But what if you actually do have one of these coefficients which is pretty, that's the truth, that everything else is the noise, and you have one or two that are really important?
Yep. So that comes out in the math, way up here. Remember those betas, which are essentially one-to-one matched with your variables, exist both in the true error calculation as well as your regularization, which means if you get rid of it, your errors are going to go up. So you're playing those things off of each other. That's how you let the algorithm manage that. So ideally, right, if you didn't care about this error term, then you would just push all these to 0. Doesn't matter their importance. But this is keeping the ones that are important up and relevant. But it has to be a strong predictor, or else it'll shrink and shrink and shrink.
So when you have multiple inputs like that, and you want to reduce the model size, you can do what they call dimensionality reduction, a couple different ways. One is you can search through and do algorithms like this where you can say which ones are the most important, which ones are getting filtered out because they're small. Or there's another way to do it is you can combine features into a super feature and have super features that represent a combination of features, and then you have a reduced set of inputs, but you're not giving up as much data. You're not giving up as much representation, that approach, and there's different ways to do that as well.
Thank you.
Okay, few things. Brian, how long are we leaving this up? All right, so roughly a week. We'll leave all your stuff up. You can go in there, you can copy your stuff out if you want, download it. This next time around that we do this, all the original files will be there, but the ones that you guys are manipulating will all disappear. So this is your chance to, right, they'll disappear. We wipe it clean. Yeah. So if you want to keep any notes you took, if you want to keep the values you did, copy and download your data. You have about a week to do that, and then Brian will take that offline. All right? Number 2, we are available by email. So if you have questions, you should ask us questions. Number 3, if you like this or you have criticism of this or whatever, let us know. We will change. If we went too slow or too fast, if we're covering a wrong topic, you just got to let us know and we will adjust. And if you say, I'm never coming to this thing again, the pizza wasn't good enough, then we'll just stop having it. So it's up to you guys. We're here to make this better. If we continue, we're going to go into more complex models, some random forest stuff. We might get into some boosting and stuff like that. Eventually, if we go long enough, we can make it to deep learning architectures, but we have a lot of work to do before we get there. Okay? Any other questions?
Thank you.
All right, thanks everyone.
If you want to access any of this at home, it's all available on GitHub. So go to GitHub, github.com, SMNIEEE. That's our GitHub page, and it's right there, ML Workshop. You can download all the files. So if you want to do that on a home computer or a different computer, go right ahead. So thanks for coming.